Ever wondered how neural networks learn to make decisions?
By the way, I already understand a lot of this stuff. I'm just trying to like refresh my memory on it, but I understand a lot of this stuff.
It all starts with
Just letting you know.
something called weights. But what are these weights and why are they so important? In a neural network, we have layers of neurons: input, hidden, and output. But the real magic happens in the connections between these neurons, where the weights come into play. Think of weights as the strength or importance of a connection between two neurons. When an input passes through a connection, it gets multiplied by the weight associated with that connection. For example, if an input value is 2 and the weight is 0.5, the output of this connection will be 1. This output then moves to the next neuron for further processing. Weights determine how much influence one neuron has over the next. During the training process, the neural network adjusts these weights to minimize errors in its predictions. This adjustment happens through a process called backpropagation, where the network learns by tweaking the weights after comparing its predictions to the actual outcomes. Over time, the network gets better at making accurate predictions. Without the correct weights, the network would be just a random guesser. But with the right weights, it can recognize patterns, make decisions,
Yeah.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, Well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants. But in these two introductory videos, you and I are just going to look at the simplest, plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the 0 and 1? It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels, the hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents, or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with the 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then, the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do
It's a sign about the user or the network. I know this, but The rate of change, delta L, delta chain rule. What's the chain rule again? Yeah, I remember that. Yeah, oh my God. So the rate of change. Something. I know the derivative is the instantaneous point of rate of change. So, yeah, you get the tangent of the line to see if it's increasing or decreasing, which makes sense. Anyhow, this will be, oh, this would be 2x. I think this would be cosine. Yeah. Yeah. have to bring your change up here. Compression derivatives. With respect to X. Hmm. This would be 3y. This would be 2x. This would be 2x, y. I think. I remember it would be like cross that out, and then would be 3y squared. You say that's 1. Okay.
Do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer, and each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases, 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many, many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra, so for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did. These values this matrix vector. We represent it by organizing all those biases into a vector, and adding the entire vector to the previous matrix vector product. Then as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing.
Okay, I get it. I get it. application. Let's give me make short test for me. Then I'll give you um, that makes a lot of sense. cosine of x. C will be damn, I forgot all about this. It'll be e x. That's not right. Yeah, that's right. Okay. You're saying you wasn't even that close. 3, yeah. Yeah. Okay. I got it.
Now is the point I suppose I should say subscribe to stay notified about when that video or any new video. Imagine you happen across a short movie script that describes a scene between a person and their AI assistant. The script has what the person asks the AI, but the AI's response has been torn off. Suppose you also have this powerful magical machine that can take any text and provide a sensible prediction of what word comes next. You could then finish the script by feeding in what you have to the machine, seeing what it would predict to start the AI's answer, and then repeating this over and over with a growing script completing the dialogue. When you interact with a chatbot, this is exactly what's happening. A large language model is a sophisticated mathematical function that predicts what word comes next for any piece of text. Instead of predicting one word with certainty, though, what it does is assign a probability to all possible next words. To build a chatbot, what you do is lay out some text that describes an interaction between a user and a hypothetical AI assistant. You add on whatever the user types in as the first part of that interaction, and then you have the model repeatedly predict the next word that such a hypothetical AI assistant would say in response, and that's what's presented to the user. In doing this, the output tends to look a lot more natural if you allow it to select less likely words along the way at random. So what this means is even though the model itself is deterministic, a given prompt typically gives a different answer each time it's run. Models learn how to make these predictions by processing an enormous amount of text, typically pulled from the internet. For a standard human to read the amount of text that was used to train GPT-3, for example, if they read nonstop 24/7, it would take over 2,600 years. Larger models since then train on much, much more. You can think of training a little bit like tuning the dials on a big machine. The way that a language model behaves is entirely determined by these many different continuous values, usually called parameters or weights. Changing those parameters will change the probabilities that the model gives for the next word on a given input. What puts the large in large language model is how they can have hundreds of billions of these parameters. No human ever deliberately sets those parameters. Instead, they begin at random, meaning the model just outputs gibberish, but they're repeatedly refined based on many example pieces of text. One of these training examples could be just a handful of words, or it could be thousands, but in either case, the way this works is to pass in all but the last word from that example into the model and compare the prediction that it makes with the true last word from the example. An algorithm called backpropagation is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not only does the model start to give more accurate predictions on the training data, but it also starts to make more reasonable predictions on text that it's never seen before. Given the huge number of parameters and the enormous amount of training data, the scale of computation involved in training a large language model is mind-boggling. To illustrate, imagine that you could perform 1 billion additions and multiplications every single second. How long do you think that it would take for you to do all of the operations involved in training the largest language models? Do you think it would take a year? Maybe something like 10,000 years? The answer is actually much more than that. It's well over 100 million years. This is only part of the story, though. This whole process is called pre-training. The goal of auto-completing a random passage of text from the internet is very different from the goal of being a good AI assistant. To address this, chatbots undergo another type of training, just as important, called reinforcement learning with human feedback. Workers flag unhelpful or problematic predictions, and their corrections further change the model's parameters, making them more likely to give predictions that users prefer. Looking back at the pre-training, though, this staggering amount of computation is only made possible by using special computer chips that are optimized for running many, many operations in parallel, known as GPUs. However, not all language models can be easily parallelized. Prior to 2017, most language models would process text one word at a time. But then, a team of researchers at Google introduced a new model known as the transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer, and most other language models for that matter, is to associate each word with a long list of numbers. The reason for this is that the training process only works with continuous values, so you have to somehow encode language using numbers, and each of these list of numbers may somehow encode the meaning of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around, all done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a riverbank. Transformers typically also include a second type of operation known as a feed-forward neural network, and this gives the model extra capacity to store more patterns about language learned during training. All of this data repeatedly flows through many different iterations of these two fundamental operations, and as it does so, the hope is that each list of numbers is enriched to encode whatever information might be needed to make an accurate prediction of what word follows in the passage. At the end, one final function is performed on the last vector in this sequence, which now has had a chance to be influenced by all the other context from the input text, as well as everything the model learned during training, to produce a prediction of the next word. Again, the model's prediction looks like a probability for every possible next word. Although researchers design the framework for how each of these steps work, it's important to understand that the specific behavior is an emergent phenomenon based on how those hundreds of billions of parameters are tuned during training. This makes it incredibly challenging to determine why the model makes the exact predictions that it does. What you can see is that when you use large language model predictions to autocomplete a prompt, the words that it generates are uncannily fluent, fascinating, and even useful. If you're a new viewer and you're curious about more
Man, Visual Studio Code is so slow. this should be good. So while that is on, I'm gonna do something else. What? Oh yeah. Oh. So wow. Nope. It's gonna take a while, so why not? Cord uses. What is he using? This is the transcript of the video. Please specify the most interesting sections from the whole. Oh yeah, I guess this is the best way to do it. How would you do that? Let's see. No. Okay. Mm, yeah. This is what I'm looking for. What the hell? Um, be right back. Yeah. It would be so dope. it? Okay, response. Good. Um, okay. I see. Mm-hmm. Mm-hmm. Should this be weights? Oh, what happened to the more thing? They took it out. Damn, they took it out. Or, yep, they took it out. Can I put the ops model? put it. I was thinking about put it. Hmm. You can't attach nothing. Oh, you can. Yeah, so actually think I just downloaded it. Let me download it. Mm. Okay. Okay, let's see what this has. right. While I wait for this, spell it right. Right. Cool. Digital ocean, is that what it's called? Oh, I just found one. And New notebook. Yeah. Is it done? Yes, finally. Absolutely insane. Come on, man.
referral link in the video. So I'm just going to click on GPU droplets here. First, we'll need to center region for our GPUs. Click on this arrow here to see the available data centers. GPU
Are you still thinking? Or did you blink?
droplets are quite new on DigitalOcean, so currently there's only 2 North American data centers, New York and Toronto. In the future, I'm sure there'll be more GPU droplets around the globe. I'm going to be going with the Toronto data center here. Next, scroll down until you see where it says choose an image. Make sure OS is selected by left-clicking on it. You can click on show all OS images to see more OS images. However, we're going to be going with DigitalOcean's AI ML Ready Image OS, which comes bundled with Ubuntu Linux. So I'm just going to click on this circle here to select it. Next, we'll need to choose a GPU plan, so scroll down until you see choose a GPU plan. Currently, there's only one type of GPU, and that's the NVIDIA H100. You have 2 plan options. You have the NVIDIA H100 X8 configuration, which means you have 8 of these NVIDIA H100 GPUs, or you can go with a single NVIDIA H100 GPU. As this is just a video demonstration, NVIDIA H100 X8 is overkill for this video, so I'm going to be going with a single NVIDIA H100 GPU, so I'm just going to click on this to select it. Next, scroll down until you see where it says add an SSH key for authentication. So when we create a GPU droplet, we'll need to add an SSH key. To do this, simply click on add a SSH key. Under public key here, we'll need to paste in our public key, but we don't have one yet, so we'll need to create a public key and a private key. The public key is what you'll paste in here and add it to your DigitalOcean account. The private key is the other SSH key, which you'll use to log into your DigitalOcean GPU droplet. To create this public SSH key and the private SSH key, what we'll need to do is open up another tab and navigate to putty.org. Once you're here, click on Download Putty. Putty is available for the following operating systems. I'm on Windows, so I'll be using the 64-bit Windows installer. Now, I already have Putty installed, so I'll be skipping the installation process here. However, if you want to see a step-by-step process to install Putty and all the other Putty tools, I'll put a link in the video description below to one of my videos, which will take you through that process. I'll also put it as a card at the top right-hand corner of this video. I also want to add, if Putty isn't available for your operating system, you'll need to download another SSH client compatible with your OS. Once you've got Putty downloaded and installed, you can minimize your browser to be taken to your desktop. On my desktop here, I've got PuttyGen and Putty. Now, when we installed Putty, we also installed automatically PuttyGen. Now, if you don't have these shortcuts on your desktop, you'll need to search for these programs using the search box at the bottom of your Windows taskbar here. Then you can simply open up the programs. PuttyGen will be the Putty tool that we're going to be using to create our SSH keys. And Putty is the SSH client that we're going to be using to log into our GPU droplet. So first, double-click on PuttyGen to open it. Now I've got PuttyGen open, which is our Putty key generator. We'll need to generate a public/private key pair. To do this, simply click on Generate, and then you'll need to generate some randomness by moving the mouse key over the blank area here. The SSH keys will then be generated. And there we go, our SSH public key and our SSH private key pair have been generated. The key displayed in this box here is in fact the public SSH key. So from where it says SSH-RSA, we're going to left click on that and highlight it all the way down to the very bottom here. Once you've got it highlighted, right click on it and click on copy. Now open back up your browser, go back to your DigitalOcean dashboard, right click on the SSH key content box here under public key and click on paste. Once you've done that, we'll need to choose a key name for this public key, so I'm just going to call it NVIDIA. Once you've done that, just click on add SSH key. This public SSH key will then be added to your DigitalOcean account. We'll now need to select it by clicking on the box here next to whatever you labeled it as. In my case, it's called NVIDIA. Now before we proceed any further, just minimize your browser for the time being to be taken back to your desktop. It is always good practice to save your generated key pairs. So I'm first going to save my SSH public key, SSH key. So using the search. Now I already have a private key. The pub create a GPU drop key is the other using the 64 video description. So installed auto the SSH generate, and then you'll need to generate some randomness by moving the mouse key over SSH keys will then be generated. And there we go, our SSH public key and our SSH private key pair have been generated. The key displayed in this box here is in fact the public SSH key. So from where it says SSH-RSA, we're going to left click on that and highlight it all the way down to the very bottom here. Once you've got it highlighted, right click on it and click on copy. Now open back up your browser, go back to your DigitalOcean dashboard, right click on the SSH key content box here under public key and click on paste. Once you've done that, we'll need to choose a key name for this public key, so I'm just going to call it NVIDIA. Once you've done that, just click on add SSH key. This public SSH key will then be added to your DigitalOcean account. We'll now need to select it by clicking on the box here next to whatever you labeled it as. In my case, it's called NVIDIA. Now before we proceed any further, just minimize your browser for the time being to be taken back to your desktop. It is always good practice to save your generated key pairs. So I'm first going to save my SSH public key, and I'm also going to save my private key. So let's start off with the public key, so simply click on Save Public Key. Choose a location, so I'm going to choose my desktop, and I'm going to add a name, so I'm just going to call it NVIDIA-Public. Once you've given it a name, click on Save. And as you can see, our public key has been saved to our desktop. Next, we'll need to save our private key, so click on Save Private Key. Now, I've been greeted with this warning message from PuttyGen, which says, are you sure you
Let me see. That's more one. I should use 0. Oh, CPU. Yeah, I'm gonna do that again. I'll take it offline. Yeah, I don't want to do this while I am live streaming. So I'm gonna do this and then tomorrow I can I can continue developing. But yeah, I'm gonna do this offline.